Welcome to your first lesson for Chapter 3. Chapter 3 is all about solving systems of linear equations. So this is a review primarily of one of the main methods for how to solve a system of equations. So we're kind of going back through some background and reviewing some concepts, also kind of reviewing how to graph some lines. But primarily Chapter 3 is all about solving systems of equations. So the first primary method that we'll be using to solve a system of equations is by graphing. And so basically what we're going to be doing is we're going to be graphing a system of equations. So first of all, a system of two linear equations is two equations with variables x and y. X and y. And they don't have to be in x and y, they just have to be both in the exact same variable. So two equations in x and y, something like ax plus by is equal to c, and then dx plus ey is equal to f. So you have equation number 1 and equation number 2. So you will have a system of equations based on those two variables. Now, I want to put this in front because we want to talk a little bit about a solution of a system. Some systems have lots of solutions, some systems have no solutions. We'll be talking a little bit about those as we go throughout the lesson for today. But really, there's each line that's graphed has a series of solutions. So here's an example of a line. Each of the ordered pairs that's on that line, for example, maybe that line is y equals 2x plus 4. Each point on that line satisfies this equation. All right. If I have some other line, y equals negative 3x plus 7, and it looks something like this, each point on this line satisfies negative 3x plus 7. And the solution to the system is that one point that both lines have in common. So visually, I know that visual will help for some of you. The solution to a system of equations is that point where those two meet. And so algebraically, it's an ordered pair that satisfies both equations. And the key word there is both. So I'm going to put that in caps, both equations. All right, it's an ordered pair that satisfies both equations in that system of equations. All right, a consistent system is a system that has a solution. It may have one solution, may have many solutions, and we'll talk more about those situations in just a little bit here. But consistent means it has a solution, and so therefore you can pretty much deduce then that an inconsistent system has no solutions. All right. Now, an independent system is a consistent system with exactly one solution. And again, we'll be going through what these mean in just a little while here, but it's a consistent system with exactly one solution, and dependent is a consistent system with infinitely many. I'll write it out, infinitely many solutions. And again, don't worry about the specifics of those, at least get the definitions down for now, and we will talk more about those when we get into the next page of the lesson. So the first thing we're going to do is we're going to talk about solving a system of equations by using a graph. And we know how to graph lines that are in the equation y equals mx plus b. Unfortunately, all of the examples that were given in this section are given in what we call standard form, what we talked about last chapter. These are both in standard form. And so to graph an equation that's in standard form, we could convert it to y equals mx plus b form, and then we'd have the y-intercept and the slope, and we'd go ahead and graph it. All right? That method will obviously take a little bit of time, and so we're going to save some time. We're going to graph this thing using its intercept. So if you recall, the x-intercept of a graph happens when y is equal to 0. So for the first equation, 4x plus 2y is equal to 4. If I want to find the x-intercept of this, that means that y is equal to 0. So if we kind of talked about this before, we said kind of cover up that y value, because when I substitute 0 in there, 2 times y is 0. So now I divide both sides by 4, and I get x is equal to 1. All right. To find the y-intercept then, we say 4x plus 2y is equal to 4. And if I want to find the y-intercept, well, the y-intercept is when x is equal to 0. So I do that, divide by 2, and I get a y-intercept of 2. So the first line, equation 1, I'm going to go ahead and do that one in blue here. That's going to have an x-intercept of 1, and it's going to have a y-intercept of 2. And so as best as I can, I'm going to try to connect these with a straight line. Again, remember, please use a ruler or some sort of a straight edge to connect your points. And there's a straight line that exists between those 2 points. And so that's an example, or that's the graph of equation number 1. Again, we couldn't do that with slope-intercept form because unfortunately our graph was not in slope-intercept form. So we had to do it a different way. All right, so let's kind of clear this out of here, and I'll do equation 2 over here on the left. 2x minus 3y is equal to 10. If I want to find the x-intercept, that's when y is equal to 0. And so my equation becomes 2x minus 3 times 0 equals 10. So like we said before, basically that term drops out. Divide both sides by 2, and you get x equals 5. To find the y-intercept, that's what happens when x is equal to 0. And so if I make x equal to 0, my equation becomes 2 times 0 minus 3y is equal to 10. Now I realize that 3 does not evenly divide into 10, but we can kind of do our best with that. We're going to get y equals negative 3.3 repeating, or negative 3 1/3. So my y-intercept is at negative 3 1/3, so that means I'm going to cross the y-axis at negative 1, 2, 3 1/3, which is roughly there. And my x-intercept is going to occur as we set up here at 5. And so 1, 2, 3, 4, 5. There's my point. And we're going to go ahead and connect those 2 dots with a straight line. And it looks like the solution to that system is like right in there somewhere. It looks like it's the point 2, negative 2. Now, obviously there's some errors and some issues with doing it this way, because especially when you go to estimate the y-intercept of negative 3 1/3, that potentially poses some issues, and so we might be a little high on our line. In here it looks like 2, negative 2 is my solution. All right, but how do we know? Well, the best way to do it is to plug 2, negative 2 into each equation and check it. All right, so we'll plug it into the first one. Again, replace the x with the 2, replace the y with negative 2. 4 times 2 is 8, and 2 times negative 2 is negative 4. Is 8 minus 4 equal to 4? Absolutely it is. Now we'll try the 2, negative 2 in the other equation. 2 times 2 is 4. Negative 3 times negative 2 becomes positive 6, and is 4 plus 6 equal to 10? Sure it is, and so the point 2, negative 2 is the solution to that system of equations. So it's a checkpoint problem at the top of the next page. Go ahead, pause your video, try that one. And we'll be right back with a solution. Okay, so solution for this one, again, we're going to do equation number 1. We'll do that one in red this time. For equation number 1, to find the x and y intercepts, because again, that's the only way we can graph this now. To find the x-intercept, we plug in 0 for y, so we get 4x equals negative 2. And when I divide both sides by 4, I get x equals negative 1/2. And so the x-intercept of this line is at negative 1/2, means it crosses the x-axis at negative 1/2. And if I rewrite that equation, 4x plus y is equal to negative 2. I substitute 0 in for x to find the y-intercept, while y is equal to negative 2, so that means it crosses the y-axis at negative 2, which is right about there. Go ahead and graph these two, or connect these 2 points with a straight line, and we have a graph of equation number 1, 4x plus y equals negative 2. Now again, you can certainly change that to slope-intercept form if you'd like to. I'm just trying to save some time and graph it an easier way. So for equation number 2 then, to find the x and y intercepts, we're going to say, look, the x-intercept happens when y is equal to 0. So if I just get rid of that, divide both sides by negative 6, I get x equals negative 2. So my x-intercept is at negative 2. All right. And then I'm going to find my y-intercept. My y-intercept is where x is equal to 0. So this becomes negative 3y equals 12. Divide both sides by negative 3, and y equals negative 4. So my y-intercept is at 1, 2, 3, 4, down here somewhere. Now those lines are running somewhat alongside of each other. But when I go ahead and connect those 2 points roughly there, I'm going to see that those two are going to hit somewhere around 1, 2, 3, 4, 5, 6. Looks like somewhere around 1, negative 6. Now again, that's an estimate from where those two intersect, so we actually have to plug that in to check it. There's no other way to verify that that is the correct solution without algebraically verifying it. So we're going to do 4 times x plus negative 6, and we're going to say, is that equal to negative 2? Well, 4 times 1 is 4, minus 6 is negative 2, and so it works in the first equation. Let's try the second. Negative 6 times 1 minus 3 times negative 6 is equal to 12. So that's for equation number 1. This is for equation number 2. So this is negative 6, and then negative 3 times negative 6 is positive 18, and so I get 12. And so my ordered pair 1, negative 6 works in both equations, so therefore is the solution to that system of equations. So we're going to get back to talking about this dependent and independent and all that kind of business like we were talking about from earlier. The number of solutions for a linear system. Linear systems that intersect at exactly one point. Again, anything that has a solution is consistent. All right, but these two lines are independent of one another, and so we say it's consistent and independent. All right. Now, if the two lines coincide, they coincide, meaning they are exactly the same line. Okay, if they're exactly the same line, like you have one line and then the other one right on top of it. If the two lines coincide, then they're consistent because they have a solution, but because the two lines are exactly the same, they depend on one another, so we're going to say they're consistent and dependent. All right, so the lines coincide, they means they're consistent because they have a solution, but because they're one right on top of another, they are dependent. All right, and then if lines are parallel, well, again, we said consistent means they have a solution. If lines are parallel, by definition, that means that they don't touch. And so if they don't touch, that means they are inconsistent. And so we would call this an inconsistent system. Okay, so if the two lines are parallel, that means they don't touch, so they're inconsistent, and so you don't have to worry about the dependent or independent because, again, consistent and independent means they are independent of one another. They have one solution. Consistent and dependent mean they're one right on top of the other, and then inconsistent means they never touch. All right, so stick that in your vocabulary somewhere for later on. We'll definitely be using that as we go throughout the rest of the lesson. All right, so example 2, it says, let's solve the system. And it says solve a system with many solutions, so you can tell that this one's going to have infinitely many solutions. Sorry, going back up to this up here, again, in this situation, these two lines cross at exactly one point, and so this has one solution. It says it up here. These two lines being right on top of another says that every point on one line is a point on the other, and so there are an infinite number of ordered pairs that are solutions, because again, if every point on one line is every point on the other line, that means the two lines are exactly the same. And this one here, there is no one xy that's on both lines. You can have points that are on this line, but they'll never be on this line. You can have points on this line, they'll never be on this line. And so those two then have no solutions. All right. So again, getting back to this example, it says solve a system with many solutions. Well, okay, so this one's going to be one that has many solutions. So this means the two lines are going to be lying right on top of another, just kind of a foreshadowing, I suppose, to kind of tell you that. So solve the system, then classify as consistent and independent, consistent and dependent, or inconsistent. So again, the only way to graph something that's in standard form, negative 2x plus y equals 4, is we have to find the x and y intercept. So to find the x intercept, that's when y is equal to 0. I get x equals negative 2. To find the y-intercept, I'm going to then plug in 0 for x. If I plug in 0 for x, that term is gone, and so I get y equals 4. So the x-intercept is at -2, the y-intercept is at 1, 2, 3, 4, and so we'll go ahead and connect those two dots, and we have a graph of the first equation. Pardon me if I don't spend enough time on how to graph a line in standard form. You need extra help with that. We've covered that quite a little bit. So I'm going through that part of it fairly quickly so we can get to the meat and potatoes of the lesson. So equation number 2 then, we're going to find the x and y-intercept there. Again, to find the x-intercept, that's when y equals 0, so this term will essentially be gone. I get 4x equals -8 rather, and so x equals -2. So I get the exact same x-intercept as I did the first time. And again, I'm going to say then 4x minus 2y is equal to -8 for equation number 2. Substitute 0 in for x to find the y-intercept, divide by -2, and you get y equals 4. And so I get the same y-intercept. And so what do you find out? You have two lines that lie right on top of one another. That means that the two lines, the graphs of the two equations, are the exact same line. And the term we used before, the lines coincide. So because the lines coincide, it says each point on the line is a solution, and the system then has infinitely many solutions. And so therefore, since it has a solution, it's consistent, and since the two lines depend on one another, it's dependent. So that means it's a consistent, consistent, I can spell, consistent dependent system. All right, so let's take a look at an example that has no solutions. Again, being no solutions, we're going to assume then that these lines are going to be parallel. They're kind of foreshadowing that for us, but we should get two parallel lines here, but let's make sure of that. The first equation, equation number 1, this is -2x plus 4y is equal to 8. So to find the x-intercept, we plug in 0 for y. We get x equals -4. All right. And to find the y-intercept then, we say -2x plus 4y is equal to 8. We substitute 0 for x, we get 4y equals 8, and so therefore y equals 2. We get an x-intercept of -4 and a y-intercept of +2. And so our first line, equation number 1, should look something like this. All right? Okay, so equation number 2 then is going to look something like this. We can find the intercepts again. -2x plus 4y equals -4. So to find the x-intercept, again, we do this. -2x equals -4. So x equals +2. I get an x-intercept of +2, which is right there. -2x plus 4y is equal to -4. Again, now to find the x-intercept, or the y-intercept rather, we plug in 0 for x. So I get 4y equals -4 and y equals -1. So my y-intercept is there. Okay, go ahead and graph these, connect these points with a straight line, and what do you see? What type of lines are those? Absolutely, those are parallel lines. It says the graphs of the lines, the graphs of the equations are two parallel lines. And since they're two parallel lines, that means that it has no solutions, and the system is inconsistent. All right. So there are a number of checkpoint problems down below here, and we're going to take a look at a few of them, but why don't you guys do just 2, 3, and 4. 5 is a little bit redundant. It's another example, but again, it's not necessary. So just skip 5 for now. Go ahead and run through 2, 3, and 4, and then we'll go ahead and we'll take a look at your solutions in just a moment here. Okay, so in example 2, again, let's just kind of run through the graphing process of this. To find the x-intercept, we plug in 0 for y. We get 3x equals -6, so x equals -2. To find the y-intercept, we plug in 0 for x, so -2y equals -6, and so y equals +3. So my y-intercept is up here at positive 3. I have to kind of guesstimate that a little bit. And your x-intercept is at negative 2, which is right in there. All right. So the first equation is going to have this kind of feel to it. Like that. Oops. I'll push a little harder there. There we go. Okay. The second line then, line number 2 in this case, is going to be negative 5x plus 4y is equal to 8. So to find the x-intercept, we plug in 0 for y. We don't get a very pretty result here, but we divide both sides by negative 5. And so we get x equals negative 1.6. All right? And negative 1.6 on the x-axis is like negative 1.6, like right in there somewhere. All right? And when I go to find the y-intercept of that one, I'm going to do 4y is equal to 8 because I plugged in 0 for x, and so this part was gone. Divide by 4, and you get y equals 2. So the y-intercept is positive 2. Now those two lines might look like they're pretty stinking close to parallel, but I'll be honest with you, they're not. So I'll go ahead and graph that line in here. And they meet down in here someplace. All right. Now, fortunately for us, it doesn't ask us to find that solution, and it's kind of hard to do that with the graph that we have here. But because these two are definitely not parallel, that means they have one solution. They're not the exact same line, and they're not parallel. So that means that they have exactly one solution. And it's right in there somewhere. Again, I'm not exactly sure what point that is. It looks like, according to the text, it's negative 4, negative 3. Yeah, that's pretty close to negative 4, negative 3. And then this would be a consistent, because it has a solution. And because those two lines are not the exact same, this is independent. All right, what you should find in number 3 is that these are the exact same line. I'm not going to go through the process of graphing them, but because these are the exact same line, this is consistent, dependent, and these two end up being two parallel lines, something like that. And so because they're parallel, this one is inconsistent. Okay, so let's get into a real-life story problem type of example here. It says, at an ice cream shop, one customer pays $9 for 2 sundaes and $2 and 2 milkshakes. So they got 2 sundaes and 2 milkshakes. The total cost is $9. Second customer pays $13 and gets 2 sundaes and 4 shakes. How much does each sundae and milkshake cost? So in the first individual, for equation number 1, customer number 1, they paid a total of $9. And the number of sundaes they bought was 2, the number of shakes they bought was 2, and then x and y are going to be the cost of the 2 items, x being the cost of a sundae, y being the cost of a shake. And so if we do $9 total is equal to 2, again, we bought 2 of them at x dollars a piece, 2 of them at y dollars a piece, we have our first equation. Our second equation, by similar argument, since they paid a total of $13, they bought 2 milkshakes and 2 sundaes and 4 milkshakes. And so we have our two equations, and so now we have a system of equations. My first equation is 2x plus 2y equals 9. The second is 2x plus 4y equals 13. All right? So in graphing the first one, we're going to get 2x plus 2y is equal to 9. The x-intercept comes out to 4.5. The y-intercept also comes out to 4.5. And you can check on your own, but you should get something like there and something like there. And so the first equation then is this going to be this red one now, and it looks like you're going to have a line something like this. All right. Now again, it only makes sense to worry about the first quadrant in this problem because you can only have positive numbers of shakes. The second equation, you're going to end up with an x-intercept of 6.5 and a y-intercept of 3.25. So here's 3.25, here's 6.5. Graph those two, and I'm just going to kind of try to freehand this. You're going to get a solution somewhere around right in there. Pardon the tone there. You're going to get a solution right around in there, which says that that's roughly 2.5 and 2. And so you would plug that in algebraically and check that solution. I won't take the time to do that. Why don't you go ahead and try the checkpoint problem, and we will go over the solution of that checkpoint problem tomorrow in class first thing.